Next in our list of contact forces will be drag. And often we ignore drag in this class, so that will continue to be the case unless you're told explicitly you have to consider it. Drag is designated as a D vector. And drag happens when you have an object and it's within some fluid. So make this some fluid. And the object attempts to pass through the fluid. And you notice this most obviously in swimming pools. When you try to swim through water, you'll notice there's a drag force, meaning you don't move through the water as easily as you move through the air. And the reason for that is you are colliding with and displacing all of the molecules in the fluid as you pass through it. And every time you have a collision, there's a third law of force between you and the molecules you collide with or the atoms you collide with. And the sum of all of those forces over your extended body creates a net force of the fluid acting on you. Drag force is then equal to 1/2 times a coefficient of drag that depends on the composition of the thing that's moving through the fluid and the composition of the fluid. So different things moving through different things have a different coefficient of drag. Multiplied by the density of the fluid, multiplied by the cross-sectional surface area of the object as it passes through the fluid. I'll explain more on that in a second. Multiplied by the relative velocity of the object relative to the fluid squared. So if the fluid is stationary, that would be the velocity of the object relative to you. If the fluid is moving and the object looks stationary relative to you, that would be the velocity of the fluid. If it's a little bit of both, then you have to just consider the relative velocity of the object in relation to the fluid. That's the thing that matters. Now, the cross-sectional area, what do we mean by that? Well, let's take a bullet, for example. Right? It has a shape like that. If a bullet were to be moving in the normal direction, so pointy end forward, then if we put our eyeball over here and looked at that, what we would see is something that looks like a circle with a tip on it, right? What we're seeing then is the cross-sectional area. So this is on a plane of that the object takes up perpendicular to its direction of travel. It's now traveling out of the page. However, if instead the object was traveling at us, then this would be its cross-sectional area. And so those are two different cross-sectional areas. The one on this one, top one, is much bigger than the lower one. And that is why bullets are shaped the way they're shaped and why we fire them in the direction that they go. We fire them in a direction that minimizes drag. So drag smaller, drag bigger. This is similar to a football. When you throw a football, it has a similar type of a shape profile. When it goes this way, minimum drag. Why? Because if you were to look at that, make this the axis that it's traveling, if you were to look at that in the direction it was traveling, it would look like this with the point pointed at you. By contrast, you could also throw the football, have it kind of facing you like this, and you could try to throw it that way, in which case the cross-sectional area would look like the profile of the football coming at you. And so this big drag, bigger cross-sectional area, this small drag, smaller cross-sectional area. Something interesting that can happen with drag is when an object is in free fall. So go back to our basketball court. We can have our hoop here. And the basketball's in the air. Well, if we consider drag, let's not do the basketball. Let's do a more interesting example. There's a phenomenon by which cats are known to fall out of windows in cities. And cities have very tall buildings, and this is how this got to be studied. And what's interesting about it is there's a range of floors, and I don't remember the exact range, where if a cat falls out of the window, it's basically guaranteed to die. So, die zone. But what's interesting is if the cat falls from a window lower, it will live. And here's what will be interesting to you, perhaps if you've never thought about this before. If the cat falls out of a window higher than that, doesn't matter how high, it will also live. It's only in this weird region of space that if a cat falls out of a window, it's going to almost for sure die when it hits the ground. And so, why would this happen? Intuitively, for us, we think the higher you fall from, the worse it's going to be. The reason for this has everything to do with drag and the reflexes of cats and how they fall. So, what happens is when a cat falls out of a window, it takes a little bit of time to orient itself. It usually does a quick little tumble and then spreads its legs out. In this die zone, the cat is kind of usually mid tumble by the time it reaches the ground. And as such, if you picture it kind of falling, it's still kind of a ball. And so the drag force is not as big as it could possibly be. And it's the longest amount of time it will be that way. And if you look at the free body diagram of the cat, then while it's falling, there's a weight force down and a drag force up. All right. Sorry about that. Technical issue. Video got cut off. So we were talking about these cats that could fall out of these tall buildings. They have this die zone is determined by the height from which they fall, which is interesting in that above or below the die zone, the cat's more likely to live. And the whole point is that this is somehow related to drag. And what this relates to is something known as terminal velocity. So as something is falling, this is where we left off. If this is the cat, then the force is acting on the cat. Well, it will always have a weight. Sorry about that. And that part's not going to change. The mass of the cat doesn't change, so the weight of the cat doesn't change. It always points down. But what happens is as the object accelerates downward due to this weight force, the drag force, which I'll write this again, is CD something like that. The most important thing to see here is that if the air doesn't really change that the cat's falling through, then all of the stuff inside the squared area is not really changing, which means that the drag force is just proportional to the velocity of the cat or you or whatever through the air squared. The one thing that is changing while the cat falls is this area, this cross-sectional area, and that has to do with the way the cat is positioning itself. Is it balled up, or is it kind of extending its arms out to make itself like a parachute? The mechanics of how the cat tends to tumble and do that has a lot to do with where this quote unquote die zone lives. At heights above the die zone and the higher live zone, the cat has time to tumble, get its legs out, become parachute looking, maximize its area to mass ratio. And what will happen is as a cat falls, initially, let's say it was always looking like that parachute, well, there'd only be a small drag force initially. So this is time going this way. But as it continues to fall, its velocity, let's make this V versus T, well, it would accelerate, so its velocity would go up. And if this was constant acceleration to gravity, what would actually happen is it would accelerate in something that looks like this. And depending on the shape it adapts while falling, there will be some threshold where the velocity will stop changing. And why will that happen? Because as it continues to fall, the drag force continues to grow. The weight force doesn't change. And eventually, you'll get to the point out here where you have the weight pointing down still, that never changed. Drag pointing up. The magnitude of weight is equal to D. And if we look at what F net should be here, well, there's only two forces acting on the cat. One points down, one points up. And we can say in the down direction, this would be W minus D. In the up direction, it would be D minus W. But either way, when they're equal, that becomes equal to 0. When F net is equal to 0, A becomes equal to 0. And that means when you reach this, V becomes constant. And we call that constant velocity a terminal. So due to the presence of air on Earth and the fact that our masses tend to take up some different cross-sectional areas as we fall, there will be a terminal velocity for all objects as they fall towards Earth. You do not continuously accelerate downward at g for forever. For the most part, for most of the things we look at, this drag force is not something we really need to consider as it ends up several decimal places past the ones you're calculating. But it is a very real effect, particularly if you go to other fluids besides air. And this is just one demonstration of a place where the effect has significant consequences even for objects falling through air.